computing at the Arizona State University, where he established and heads the Make Programming Simple lab. He completed his PhD and MS in Information and Computer Science from the University of California, Irvine, and Bachelor's in Computer Science and Engineering from IIT Delhi. So his research is on making programming simple for embedded and cyber-physical systems. And as I mentioned before, many of you may know him because he has been very active at LCTES and related events. So Aviral, the floor is yours.
Thank you, Geronimo. And thank you, JJ, for inviting me here. I think it's my true honor to present at this location. So I know this is a conference on embedded systems, and I am talking about quantum computing. So this may seem like a mismatch, but you will see as we go through this this talk that actually quantum systems are inherently embedded, very resource constrained and embedded in that sense. And so we can apply a lot of our learnings and technologies to this domain. Okay, so let me start by first thanking all my co-authors here who are the real brains behind this work, and I am just the face of them. So I hope I can do justice to them, this work, and to you guys who have thankfully woken up early in the morning and come to the talk. So thanks a lot for being here. Okay, so this is the outline of my presentation, and essentially I have broken this down into two parts. The first three sections are kind of tutorial style, and so they should be really easy to follow, and the next three sections are a bit more researchy, right? So the first three sections I really want you to understand completely, and if you have any questions, please feel free to ask. This small workshop style nature of this conference allows us to be interactive, right? So please feel free to stop me anytime and ask a question. So in my mind, if we just understand the first three topics, I think we are in very good shape, right? So that would be a great achievement. So with that, let me start. So I'll start slow in with the background that most people have at least designed some ML models, right? So if you have designed even a few ML models, most probably you have made a classification model, right? So classification models are the ones that you give a dog image and cat image, and it can tell you whether it's a dog or a cat. So how do they work? So there is a neural network which is essentially just matrix multiplications and then layers of some nonlinear functions, right, like softmax or ReLU. And then the size of the input layer is equal to the size of your input. So for example, for this is for MNIST, right? So for MNIST has these images of these numbers. So they are 28 by 28 pixels. So that is 764 values. So the input layer size is 764, and the output size is equal to the number of classes that you have, right? So there will be 10 outputs, and so after this computing, you will get 10 outputs, and then we run a softmax layer on top of them. And what that does is that it takes these values and converts them into a probability distribution. So the relative ordering of the data remains the same. The higher number is still higher and lower is still lower, but they just start adding up to 1, right? And then on this we compute this cross entropy loss. This is the key for classification models, right? So the cross entropy loss is the loss function is the one that actually drives the whole training, and what does the network learn. So cross entropy loss function is actually just trying to check. So you generate 10 values, but and each value says like what is the probability that the input data is 0 or 1 or 2 or 3 to 9. So the cross entropy loss function forgets about every other output, it only looks at the output of the correct class. So, if you gave a 3, right, the correct class was 3, then it looks at the output of the 3 class, and 1 minus that value is essentially the loss function. So, what you want is that if your probability that if your network is predicting that the probability that this is a 3 is 0.1, that means you are very far away from truth, and what you want is that the probability should be close to 1, and then the loss is low, and then your network has learnt. So, essentially this is the basics of a classification model, right. So, no questions till now, right. So, this works well for classification, but there is a lot in terms of geometry that is left to be desired, and this is a crucial point here. So, one is if you can see at the top right diagram, cross entropy loss function, what it does is that all it is trying to do is to create boundaries between these data points, so that the data is in the right region, right. So, that is one way to think about it, but actually the right way to think about it is that this cross entropy loss function is mapping data from one vector space to another vector space, and so every layer of this neural network keeps mapping to a new vector space until those points are in the right region. In fact, for a cross entropy loss function, the boundaries are already pre-decided. So, if the probability is greater than 0.5, then it is that class, right. So, actually the cross entropy cross function is not trying to define boundaries, it is trying to map the data to the right place, and that is what the weights mean, right. The weights are actually transforming from one vector space, mapping data from one vector space to another vector space. So, I think that is clear. So, the cross entropy loss function has a major limitation that actually it only cares about moving the data to the right region. It has no concern about where the data is in the region, right, and this creates some weird problems in the sense that actually a yellow point which is from one class can be closer to a green point than to another yellow point, right, which in a sense does not make a lot of sense, because all of those yellow diamonds are one class, right. For example, number 3, while greens may be number 1. So, a 3 should be closer to 3 than to 1, and this concept is actually the key of metric learning. So, metric learning is the whole idea of metric learning is that distances in the feature space should correspond to semantic similarity. And that is the key distinction that we want to achieve, and what we would like to have is a space like that on the right one. Geometrically, we would like these points to be arranged like in the right image, where the mappings of objects of the same class are close to each other and they are away from the mappings of another class. And actually this has a lot of benefits if you can do that. For example, one very strange problem of classification models is that the classification model actually divides the entire space that there is among the classes that you have defined. So, if you have defined 10 classes, then entire space will be divided into these 10 regions. So, now what happens is that if you give any other image, right, it will, even if it is not from one of these classes, it will map to one of these classes, right, because there is no space left. So, and what you can see is that what we want is the geometry on the right, where objects of the same class are mapped close to each other in clusters, and so there is actually space outside the clusters that is free. So, if a new kind of object you give as input, then most probably it will be mapped to an empty space, and then you can detect that as a out of distribution data. So the left side is the kind of geometry that we achieve in the latent space or in the feature space by classification models, but on the right side is what we actually desire. Right? And what we desire, the fundamental key desire, is that the distance between the mappings of same objects, right, should be less, and the distance between mappings of different objects should be more, in the sense that distance should reflect semantic similarity. So this key idea is called metric learning, and it is achieved by this loss function. And there are many other loss functions as well, but this is a key loss function that that achieves this this property. And you can see the first thing you can see from this loss function is that this loss function is not defined in terms of the class of an object, it's defined in terms of distances between the mappings of the objects. Right. So, distance between the mapping of x a and the mapping of x b. Right. So, how a metric learning pipeline works is that, so this special case is this triplet learning. In this, we take a data from one class x a, and then we take another data from the same class, we call it x p positive, and then we take a data from the negative class, we call x n, and we pass them through the network, and this network then maps them to a latent space, right. So, we can call them z a, z p and z n, and then we calculate the distances between this z a, z p and z n, and actually these x's should be z's, right. So, that is clearly wrong, but how this triplet loss function allows us to achieve that kind of clustering, you can see from here, is that so loss, so one term in this loss is distance between the anchor and the positive, right. So, if this is low, then your loss will be low. If this is high, then loss is high. So, that means what this cost function or loss function wants is to reduce the distance between the anchor mapping and the positive mapping. And then the second term is m minus distance between the anchor and negative, right. So, that means you are trying to reduce increase the distance between the anchor and negative to at least m. So, if the distance is less than m, then you have a loss, but if the distance is more than m, then actually you get a negative number, m minus d is a negative number, and then your but because you are taking max with 0, so then your loss becomes 0. So, this causes a pull and push effect where the mappings of the same class get clustered together, and they are clustered away from objects of different class. And this fundamental rule that the distance between the mappings reflect the semantic similarity works both inside a cluster as well as outside the cluster. So, you can say that the green objects are more similar to the red objects rather than the blue objects, right. And in practice, it would be like the mappings of cats is closer to the mappings of dogs than to mappings of elephants, right. So, okay, so we want to do metric learning. So, how do we do this? What is the requirement to do metric learning? So, let us go back to classification problem first. So, in classification problem, if you want to solve the optimization, then you need to work in vector spaces. Why vector space? Because vector space means that every element is a vector, and you are allowed to subtract these vectors and also multiply them by a constant scalar. So, you will need that to compute, to do the gradient descent, right? Otherwise, you cannot compute Wt plus 1 minus Wt, right? And you cannot multiply by a scalar the eta, the learning parameter. So, to be able to do this, you need this to be a vector space. But that is not enough. We also need it to be continuously differentiable, in the sense that at all places you should be able to differentiate the loss function with respect to the weights. So, this kind of a space is a continuously differentiable vector space. Now, by definition, this vector space does not have a definition of distance. So, definition of distance comes from metric spaces, and that is why this name of deep metric learning, the metric comes from this definition of metric spaces, which is essentially a set where there is a definition of distance. And there can be many definitions of distance, many are allowed. The only requirements for a definition of distance is that distance should always be positive, and if you take a vector and multiply it by a scalar, the length of that vector is equal to the absolute value of the scalar times the length of that vector. And it should follow the triangle inequality. The triangle inequality is the one that actually gives space to structure to the manifold of the data, because what it says is that the shortest distance, the straight line distance, is always the shortest. So, Zi plus Zj will always be less than the length of Zi and length of Zj. So, you can think of this acting in terms of that if you have two red dots and a blue dot, and the blue dot is farther away from the red dots, right. So, let us say it is at least m distance away from the red dots. Then what this triangle inequality does is that it creates a circle in 2D space, it creates a circle around this red dot of m radius, and the blue dot can only exist outside this circle, right, while another red dot could be closer. So, essentially this triangle inequality is super important, and it creates the structure in the space. Okay. Next point. So, before we formally define the requirements of what is required for metric learning, one very important part is that is the need or mandate for high dimensions, and this comes from this Covers theorem, and it is actually very intuitively explained by this experiment at the top. So, what this is that you have a 2D space, and you have these green points and these red points, and this is very classical data set, it is called concentric circles. So, in this two-dimensional data, if you want to classify them, that means you need a one-dimensional line, right, to separate them. But there is no one-dimensional boundary that you can create that will classify this data correctly. So, what Covers theorem says is that it becomes easier to classify if you project this data in a higher dimension, right. So, what we do is create another z axis, and the z coordinate of every point is equal to the radius, the distance from the center of that point. So, if you can map it this 2D data into 3D, then you can very easily now create a horizontal plane, and all points below this are green and all points above this are red. And essentially that is what this Covers theorem is saying, that it becomes easier and easier to classify data or find a separating boundary if you project the data in higher dimensions. So, this is key. So, coming back to what are the requirements for metric learning. So, metric learning, what you want is higher number of dimensions. The higher number of dimensions you can have, the better the separability of the data you can achieve. You want a distance metric, right, and because as you saw, the loss function actually contains distances, right. So, you have to calculate the loss, you have to calculate distances, and it is a function of distances. So, if you can have a quick way to calculate distances, that would be great. and third is that it must be differentiable everywhere. Right. So, these are the key requirements for metric learning, and metric learning is now the cornerstone of all ML technologies. So, for example, the word2vec, clip, right, all of these are already pre-designed metric learning models and actually mappings that that generative AI is built on. Right. So, this part, to conclude this part, as in this is classification models are good, but they do not enforce very good geometry on the latent space. So, the geometry that we desired can come from metric learning models, but metric learning needs a distance function, and so it needs a continuously differentiable normed vector space. And so, what you would desire for good metric learning is high number of dimensions, continuous differentiability, and a native or quick distance calculation function. Right. So, this finishes the first part of my talk, which took double the time that I thought. Okay. But I hope this part is clear, right, to everyone. So, then no questions. Okay. So, now let me delve a bit into quantum geometry, the promise of quantum geometry. So, the whole point of this section is that I am trying to show you that quantum geometry actually provides very good solutions to all the three requirements of a good metric learning approach. So, it gives you very high number of dimensions, it has a native distance calculation metric, and it is continuously differentiable. So, that is the goal we want to reach after the end of this section of the talk, right, because those are the three desires for good metric learning approach. So, this is where we are trying to reach. Okay. So, let us start simple again. What is a qubit? Right. So, and to understand that, let us backtrack one more step. What is a bit? So, bit is a piece of information and it can be in state 0 and 1. Most crucially, you can think of an internal state of a bit and external state of the bit. So, externally when you read a bit, it is, you will read it as either 0 or 1. An internal state of the bit is same as the external state of the bit. So, if the internal state is 0, you read 0. If the internal state is 1, you read 1. A qubit is different in the sense that its internal state is different from the external state. So, internal state of a qubit is a 2 cross 1 vector of complex numbers. So, it is alpha beta, where alpha and beta are both complex numbers, with a limitation that alpha square plus beta square is equal to 1. So, what is alpha square? Alpha square means, where alpha is a complex number, alpha square means alpha times alpha star, which alpha star is the complex conjugate of alpha, right. And so, then you can say that if A, and what is complex conjugate? So, if alpha is A plus IB, then alpha complex conjugate is A minus IB, and then you can see that alpha star alpha is A square plus B square, which is a positive real number, right. So, so alpha square of a complex number is always a positive real number. Okay. So, the internal state of a qubit is actually very, very rich. It is not just binary 0 or 1, it is 2 complex numbers. So, one can be 3 plus 2i, another can be 4 plus 6i, right, as long as they follow the normalization constraint. But you can see it is 2 complex number, each complex number is comprised of 2 real numbers. So, there are 4 real numbers inside a qubit state. So, it can have infinite possibilities. I mean, even one real number can have infinite possibilities, but these are 4 real numbers. So, there are it is a very rich state, but the challenge is that whenever you read it, you will read it as either 0 or 1, right. So, the external state is still very limited, while the internal state is very rich. Okay. So, we understand that qubit is a 2 cross 1 vector, and like any vector space, there is a basis of that vector space. So, the simplest basis of this vector space is this 1 0, and that other one should be 0 1, right, 1 0 and 0 1. And then you can see that any vector in this vector space can be represented as a linear combination of the basis states, right. And in quantum computing, this Dirac notation is very popular, and actually once you get used to it, you realize it's brilliant in terms of when you are operating with vectors. So, it's very easy. This is a weird symbol which is, so this is called the ket of 0, and this is a column vector 1 0, and ket of 1 is 0 1, and we write an arbitrary state like alpha beta as a ket of psi, which is equal to alpha times 0 plus beta times 1, right. So, you can see that, so this ket of 0 and ket of 1 are the basis vectors, and you can represent any general vector as a linear combination of these basis vectors, except that the coefficients of the linear combination can be complex numbers, right. So, that is a bit of a complexity. So, then along with this ket, we also have a bra notation. So, bra of psi is actually the conjugate transpose of the ket vector. So, alpha, so this psi was a 2 cross 1 vector alpha beta. So, so we need to take conjugate transpose. So, first transpose it, so it becomes a 1 cross 2 vector, and then you conjugate it, so it becomes alpha star beta star, right. So, a row vector of alpha star beta star. And then what you can easily see is that if you multiply these two together, right, with bra first and ket later, then that comes out to alpha star beta star times alpha beta, and that is alpha star alpha plus beta star beta is equal to 1, which is the same as the normalization constraint at the top. Right. Okay. So, where are we? So, we understood that the states of a qubit are a 2 cross 1 complex vector, right. So, if you think about it, it is a 2 cross 1 complex number. Each complex number is made up of 2 real numbers. So, that means there are 4 real numbers, and there should be 4 degrees of freedom, right. But actually, because of normalization constraint, 1 degree of freedom goes away, and there is a unique property of quantum systems where a state and a scalar multiple of the state actually means the same thing. So, a state psi times is the same as another scalar constant c times psi, right. So, that because of that you lose another degree of freedom. So, essentially what it comes, so that means there are only 2 degrees of freedom left. That means that this this state of a qubit is a surface, right. So, actually it is a surface, all the states reside at the on the surface of a unit sphere, right. And you can write a general state as in this form, cos of theta by 2 0, ket 0, and e to the power I phi sin theta by 2 ket 1. Why? Because as you can see this in 2 ways, right. One is that this cos theta by 2 is the so 0 and 1 are the basis vectors, and cos theta by 2 is the coefficient of 0, and e to the power I phi sin theta by 2 is the coefficient of 1. So, this is a linear combination of 0 and 1, right. And you can also see that actually that because this is a point on this unit sphere, right. So, the coefficient of 0 can be cos theta by 2, and the coefficient of 1 can be sin theta by 2, so that when you square this, it will become 1, right. So, that cos square theta by 2 and plus sin square theta by 2 will be equal to 1. Okay. So, the point is that that all the qubits live on the sphere, on the surface of a unit sphere, and their general state can be written as this. So, most crucially, theta can have a range from 0 to pi, and what is theta? Theta is the polar angle, right. So, the angle from the z axis, and phi is the angle from the x axis. So, theta can have a range from 0 to pi, and phi can go around the entire x y plane, right. And by choosing any value of theta and phi, you can access any point in this block sphere, right. Okay. So, this makes sense. Now, so this is a vector space, and now we need a metric of distance here, right. So, how do we get a metric of distance here? So, actually there is an inner product that is defined on this space, because this is actually the qubit state is not only an inner space, but actually it is a Hilbert space, and there is one more step that I skipped. It is actually a projective Hilbert space, but let us not go into that complexity. But in an inner space, there is an inner product that is defined, and inner product of two vectors psi and phi is actually the bra of one vector times the ket of another vector. So, you can calculate it like this, and then you can see that the inner product of a vector with itself is always 1, right. This is we saw this in the last slide. What it means is that the length of all vectors is 1, right, and that's why they are all reside on the surface of a block sphere. So, then but using this inner product, we can define a fidelity function, which is actually this inner product square, and that gives us also a definition of angle between two states or fidelity between two states. Fidelity, but by the nature of this, actually fidelity is opposite of distance, in the sense if the fidelity between, if you take if the states are same psi and phi, then fidelity will be 1, and if the states are orthogonal, then the fidelity will be 0, because that is how cos alpha works. So, we can actually define a distance metric by subtracting it from 1 by reversing that function, and essentially with this distance function, which is defined using fidelity, distance between similar states is less and distance between different states is more, right, and the distance is in the range of 0 to 1, that is it. So, this gives us a distance metric. Okay. The next, so we now know that the qubits are the qubit states are actually vectors, right, on a unit sphere. So, now what do quantum operators do? Quantum operators actually just change the state. So, they rotate the state. So, you can think of all the gates just in terms of these three fundamental gates: Rx gate, Ry gate and Rz gate. Rx gate rotates the state around the x axis, Ry gate rotates the state around y axis, and Rz gate rotates the state around z axis. So, there are many more gates and all that, but you can think of all that the gates do is just rotate the states, and you can rotate from anywhere to anywhere using just these three gates. In fact, actually you can rotate with just two of these three gates, you can pick any two, right. Okay. And another thing that I want you to see is that, so what are these gates? These gates are actually just matrices, right. So, and how do you apply, so our vectors were 2 cross 1 vector. So, these gates, quantum gates are 2 cross 2 matrices, and how do you apply a gate to a state? You multiply it from the left. So, essentially where is the pointer? Here it is. Yeah. So, if this u is the gate, which is a 2 cross 2 vector, and psi is your state, then you multiply u from the left, and that gives you the new state psi prime, right. And there are some restrictions that not any matrix can be a gate, only unitary matrices are allowed, and what it means is that there are two big implications of that. Unitary matrices mean that u dagger should be identity. Again, dagger, what is dagger operation? Dagger is transpose conjugate. So, you take a matrix, you take its transpose, right. So, make rows into columns and columns into rows, and then take the conjugate. So, that means take complex conjugate of each number. So, that is how you get u dagger, and u times u dagger should be identity. So, the two implications of this being a unitary matrix is that, one, that it preserves the length of a vector. So, when you apply u to psi, you get psi prime. The length of psi prime is same as the length of psi, right. And this is very useful because our states were unit vectors, right, vectors of length 1. So, after applying any gate, they still remain a vector of length 1. So, that means the state is still on the surface of the block sphere. Then second property that it has is that it is angle preserving. That means, if you have two vectors, you apply u on them, then they both rotate together. So, it preserves the angles between them, right. Okay. So, this is one very important property, that quantum operators only do rotation, and they do like a solid rotation. They do not rotate different vectors by different amounts, they rotate everything by the same amount, right. Then second important thing is that all quantum gates are infinitely differentiable. So, a quantum gate like this Rx gate is written in terms of sin theta and cos theta, and you can differentiate it. Sin theta will become cos theta will become minus sin theta, and you can keep differentiating it indefinitely, right. So, this satisfies our important property that we want a continuously differentiable loss landscape, right. Okay. Now, this is another slide which says how do we measure. So, this is actually fascinating. So, what we saw is that the defining property of quantum of qubits is that the internal state is very rich. It is made up of two complex numbers, but externally it is binary, right. So, how do we achieve that? By math, right. So, what happens is that all the measurement operators are actually Hermitian matrices. So, when you have to measure a state, you can only measure it by a Hermitian matrix. So, what is a Hermitian matrix? Hermitian matrix is one in which H is equal to H dagger, right. So, again, what is the dagger operation? Is the transpose conjugate or conjugate transpose. So, first you take the transpose of the matrix and then conjugate every element. So, if a matrix has to be the same as its transpose conjugate, that means at least its diagonal should be real numbers, right, and it should be a symmetric matrix. So, this is one property of Hermitian operators, Hermitian observables. Okay. Now, how do we measure? So, if we take a operator and we give it a state, say psi. So, we have an operator here z and we get a state psi, then the only values you can observe are the eigenvalues of this Hermitian operator. So, in specific, this observable z is 1 0 and 0 1, 0 minus 1, its eigenvalues are 1 and minus 1. So, the only things that you can observe when you read any state, whatever be alpha beta, right, whatever be psi, you can only read 1 and minus 1. And when we talk in computing, we actually convert this to 0 and 1. 1 is converted to 0, and when we say state 0, that actually means that we read 1, and when we read minus 1, then we say it is state 1, right. So, but that is just the binary issue. Okay. Now, the other property of quantum mechanics is that as soon as you measure a state, right, that state collapses to the corresponding eigenstate. So, for example, so now we can understand the whole measurement process. So, the observable is Z, its eigenvalue is 1 and -1, the corresponding eigenstate of 1 is 1 0 or 0, and the corresponding eigenstate of -1 is 0 1 or 1, right. So, if you get a state alpha beta and you read it, you can only read one of these two values, either 1 or 0. If you read a 1, the state will collapse to 1 0 or the 0 ket 0, and if you read -1, the state will collapse to 0 1. So, the state, so measurement is destructive in the sense, right. So, it changes the state. Now, so you can read these two values and it is statistical in nature, right. So, what do you read? So, you can read 1 or -1, but with what probabilities? So, you will read 1 with the probability of alpha square and you will read -1 with the probability of beta square. So, essentially to calculate that, we calculate the fidelity. So, the probability of reading one of the eigenvalues is a measure of fidelity of your incoming state with the eigenstate, right. So, you can see that measurement actually evaluates the fidelity, right. So, the probability with which you will read 1 is equal to the fidelity of the two states. One of them is your input state and other one is the eigenstate. So, this is again towards our property that we want a matrix, we want a system in which the fidelity or distance can be measured natively. Then this is probably the most fascinating aspect of quantum spaces, quantum geometry. So, what does the state of a multi-qubit system look like? So, we saw that a state of 1 qubit can be represented by a 2 cross 1 complex vector, right. So, to figure out the state of a 2 qubits, we actually calculate the Kronecker product of the two states. So, which is the second vector is multiplied by each element of the vector. So, you can see that in operation and then you get a 4 cross 1 complex vector, right. So, what you can see is that so for a 1 qubit system you have 2 cross 1 complex vector. For a 2 qubit system you would have a 4 cross 1 complex vector. For a 3 qubit system you would have a 8 cross 1 complex vector, and so for an n qubit system you have a 2 to the power n cross 1 complex vector. So, that means the dimensionality of your space is increasing exponentially with n. So, you have 10 qubits you get a vector of 1024 complex numbers, right, and with 50 qubits you can have a state which has dimensions which are larger than the number of atoms in the universe, right. So, the dimensionality increases exponentially. So, we fulfill all the 3 promises of what we want in a very good metric space, right. Quantum space provides exponential dimensionality, it provides a native distance engine, because whenever you measure the probability of measuring a 1 is a measure of the fidelity, right, and it is all the operators are infinitely differentiable. So, you can calculate your loss everywhere in the landscape. Okay, this is a good time to stop. So, any questions, because these two are kind of heavy things, although they look simple. Any questions? No? Okay, so clearly we can't finish the whole talk today. So, we will just do one more section and then stop there, right. And I think which is also very instructive, as I said, I mean if we can just cover the first 3 sections, that would be great. right? Yes, please.
I wonder if you introduce the distance equation? Distance for similarity.
Yeah, so distance is, I already showed that equation. This is the distance between two states.
My question is that standard for quantum geometry domain or
This,
any other variables?
that's a very good point. So, actually, for a metric space does not define a distance metric, it only requires a distance metric, and any distance metric is okay as long as it satisfies three properties. One, that the distance is always positive. Second is that scalar multiply works, right? And third is the triangle inequality. Any distance metric that satisfies these three properties can be used for metric learning. And this is just one of the distance metrics. There can be many others. Perfect. Thank you for a good question. Okay. So, now the only other section that we will go over is how can we now create a quantum metric learning architecture, right. So, this is also just the basics of how we can do this. So, we will start from a naive approach, what an ML engineer would start doing, and then see what are the problems in that and see if we can solve them. Okay. So, in my mind, if I were an ML engineer, not an expert ML engineer, just a beginner ML engineer, then this is how I would design a quantum metric learning pipeline. So, I will take the input data, but input data like this MNIST image is classical, right. So, I need to convert it into a quantum state, right. So, that is the first step, data encoding. Then second step would be to create a parameterized circuit, right. So, parameterized circuit with parameters theta that we can train, right, and improve the separability of the data, right. And then we need a way to measure the distance, right, and then using those distances we will calculate the loss, and then from that loss then we can calculate the gradients, right, del L by del theta, right, and then update the parameters theta, right. Does this make sense? This is how you would make a metric learning pipeline. So, let us go into each stage and see what are the challenges and what we need to fix. So, first is how do we do data encoding, right. So, actually we can use the rotation gates that we have, right. Rotation gates take a parameter theta, how much to rotate, right. So, you can rotate by that. So, typically we draw quantum circuits from left to right, where left is the input, then there is a gate, and then the parameters come from the top, and then the output is on the right side. So, we can use this RY gate for example, or RZ gate or RX gate, whichever rotation gate you want. This will rotate and create a state, and that state will be data dependent because it is xi is the parameter. The only challenge here is that the rotations have periodic nature, right. So, if you are rotating, for example, if this was the RY gate, then theta can only go from 0 to pi. So, that means you must scale all your data to be between 0 and pi, and then you can create unique states for all your data, right. Does that make sense? So, no problem here. I think this is pretty straightforward. Okay. Second, so now we need a parameterized circuit. So, now we have encoded this data, and we need a parameterized circuit that will increase the separability as we train this theta, as we pick this theta. So, here there is a fundamental problem. Actually, whatever theta you pick, we saw that actually quantum gates are like rigid rotations. They cannot change the angles between the data points. So, actually this parameterized circuit will never work. whatever is the separation between the data will remain the separation between the data. It can rotate and all that, but it cannot change the separation. So, to separate the data, we use a data re-uploading ansatz. So, ansatz is just a fancy name quantum computer people use for describing a circuit. So, essentially it is a circuit, right. And it is data re-uploading in the sense that, so there is a layer that is the parameterized layer, and then there is a data layer. So, there is some gates. So, you again rotate using the x parameters, so your inputs. So, by alternating this parameterized theta parameterized gates and data parameterized gate, you can actually achieve separation of data. JJ. Yes. Yes. Right. So, we are doing metric learning, right. What we want is that the data comes in, we want to separate them, right. So, you can think of it as I think it may be this, yeah. So, I am getting say maybe zeros and ones, let us just think of binary, right, 0 and 1, then zeros and ones get encoded on this block sphere. If I have trained it correctly, then all the zeros should come at the top and 1 should come at the bottom. So, I want to increase the separability of the data, right. But if I do not have data dependent gates, then you cannot change the separability, they all move together. So, how does data dependent gates actually enable separation? You can think of it like this. So, for example, your data is 10 and 20 in very simple terms, degrees, right. So, so the 10 one will rotate by 10 degrees, 21 will rotate by 20 degrees, right. Now in the next step, when you do it again, then again the 10 one will rotate 10 more degrees, so it will go to 20 degrees, but the 21 will rotate 20 more degrees and go to 40 degrees. So, now the separation is doubled. So, by interleaving these quantum parameters and data dependent layers, you can actually change the increase the separability. Okay, only 5 more slides left. Yes. They are quantum gates, they are just rotation gates, but they are parameterized by data rather than parameterized by trainable parameters, right. So, let me go back here again. So, you can see, so our layers are formed of W layers and V layers. W layers are parameterized by the trainable parameters theta, right, and X layers are parameterized by the data. So, that is why this is called data re-uploading. Okay. Then our next part, and this is where it gets more interesting. So, our next part is that we need to calculate distances and we need to calculate loss, right. Okay. So, we said that distance in quantum geometry is the metric we are using is the fidelity, right. And so, when we measure the probability of you read only 1 and minus 1, the probability of reading a 1 is a measure of the fidelity. But the problem is that you cannot do one measurement and find out this probability. Finding out this probability is a statistical exercise. So, you need to do several experiments, imagine like doing 100 experiments, and then you see that 70 times you get 1 and 30 times you get minus 1, and then you will say, oh, probability of getting a 1 is 70%, and then you can say, okay, that is a measure of the fidelity between the two states, right. So, that is the challenge, and you have to do several shots of this execution, typically more than 1000, between 1000 and 10,000 shots you have to do, and then you calculate the number of experiments when the output was 0 and divided by the total number of experiments, that is your measure of fidelity, right. So, I am overlooking a couple of things. For example, when we do a measurement, you calculate the fidelity between one of the eigenstates of the observable and your given state. So, there is a swap test circuit that you can make, and we can discuss this offline, but essentially what it does is that given any two states, it projects the fidelity between these two states to the probability of you reading a 0 in the first qubit, right. So, all you need to do is to make several observations and see how many times the first qubit is 0, right, and that is your measure of fidelity between the two states. But so now you have to do these shots, right. But once you compute the fidelity, you can compute the loss function pretty straightforward, right. Except you can see that in this I changed the signs of AN and AP, fidelity of AN and AP, because fidelity is inverse of distance. So, this is the correct formula. Okay. Then gradient calculation, right. So, how do we calculate gradients here? So, the problem is that yes, the gates are infinitely differentiable, but you cannot access the state inside the quantum computer. At the end of the day, you give this input x as the input, and all you read is when you do the measurement, you can read what is the output state, right. So, you cannot do back propagation as we do in classical computers. But fortunately, there is actually a simple way to calculate the gradient, calculate the exact gradient delta L by delta J by calculating the loss at the parameter plus pi by 2 and loss at parameter minus pi by 2 and divide by 2. And intuitively why this works is because any loss function can be actually written in terms of cos theta and sin theta, and so you can see that derivative of this is the cos is replaced by sin and sin is replaced by cos, and by doing theta plus pi by 2 and minus pi by 2 also does the same thing. So, you can calculate that function using these two functions, right. So, now to calculate the gradient, you need to do two experiments. Run this circuit with parameter theta j plus pi by 2 and parameter theta j minus pi by 2. So, this increases two more shots, and now these two effects are multiplied with each other, right. So, this is the final QMeL flow that would actually work, right, and give results. So, essentially we take the data, we scale that data, we use the rotation gates to encode that data, then we have a learnable circuit which is a data reuploading circuit, and we run this for every pair of xa and xp and xa and xn, and for each parameter theta j, right, we have to run this, and for each parameter we have to run theta j plus pi by 2 and theta j minus pi by 2 and do the swap test here, and then collect the number of zeros that you get in the first qubit, and that gives you the measure of fidelity between the encoded states of these two, and that you can use to calculate the gradients, and then you can update the parameters. Okay. So, this is extremely compute intensive, right. This requires 4 into p into n shots to do one step of gradient update. So, very bad, right. So, n shots is about 1000, and then p is the number of parameters that you have, and 4 is because you have to do 2 times for each one, and then you have to do for xa and xp and xa and xn. So, I will stop here. So, hopefully what you got is a insight of what is needed for good metric learning, why quantum geometry provides a very good geometry for quantum metric learning, but there are many issues if you just want to do it directly. So, actually the work that we have done enables us to do quantum metric learning without falling into any of these traps. So, we did not have time to go into the solution, but you can read our paper, and but hopefully you can you reached here.
Yeah, thanks, Aviral. So we still have time for some questions, some further questions.
I don't know whether you make this a bit limited to the quantum metric, to the metric learning, because it looks to me that original problems are relevant to clustering and also other partitioning problems of the data, right? So is that on purpose, or you somehow try to focus only in this talk based on that?
No, I think we don't realize, but actually all AI is almost, metric learning is a very big part of AI. So, metric learning is very important by itself, even though we start learning from classification models, the real learning is in metric learning. So, so that is why.
Very good talk. I was very interested in this, the quantum computing. I'm kind of new to this topic, by the way. I was really looking forward to hearing more about your research outcome. So can you just deliver more the sentences?
So actually, let me give you some highlights of our results. So actually, there is a quantum metric learning tutorial on Google Circ, because Google makes a quantum computer and they have a programming language to actually program that quantum computer, that is called Circ. So there they do actually metric learning with 2 by 2 images. So they just 2 by 2 image, just 4 pixels, right, because this does not scale. In contrast to that, our approach, actually we can do complete MNIST, we can do omniglot, we can do multimodal learning. All of this is enabled because we figured out a way to learn in quantum Hilbert space while avoiding all these pitfalls. So I think the biggest contribution of this work is in scaling quantum metric learning to realistic problems. It is not still comparable to classical learning. So that is not the approach. I think classical metric learning is very advanced, and we are still learning how to do quantum metric learning. And if you look at all the papers that are there in quantum machine learning field, they all use very limited data sets, like the concentric circles data set or binary data sets and so on. So one of our biggest contributions is that we have been able to scale it up to at least realistic levels of problems.
Right. I had a similar question, maybe for us to get a sense of how you do this first encoding. So you gain the dimensionality because of the qubits, right? So the amount of qubits gives you a space of 2 to the n, right? But then you start with an image, like this one right here, MNIST, maybe with 256 bits, right? So an 8 by 8 image. So you have 256 bits in the image.
So this has 28 cross 28, right? 764.
All right, 28 times 28, that's classical bits.
Yes.
But I guess you have to reduce it into qubits. So actually you reduce the dimensionality into the qubit encoding. Can you say more or less how is this scaling more or less working? So
actually this ultimately in our solution, these images can be converted into 6 qubits.
6, okay.
So they can be, their state can be expressed in 6 qubits. Actually, if you think about it, qubit can hold a lot of information. Yeah. 1 qubit could actually encode everything, right? Yeah. Because it has infinite possible states.
Yeah.
But yeah, I think the separation and your accuracy of measurement and all that come into play.
Because I was wondering about the scalability, and with 6 qubits, I mean, you can imagine a quantum computer with 6 qubits.
Correct.
And then maybe final question, if nobody else. So then you have to do all these rotations, and I guess there's going to be some physical constraints in the granularity at which you can do these rotations. Is that a problem at all or not? Or
so that's actually a very important constraint, and this is, I think, all embedded people can relate to, is that quantum computers, as you know, they have very few qubits, right? So even the best quantum computer has only 50 usable qubits for now, right? And their circuits cannot be very deep because there is noise and decoherence that happens. So you must compute in a very shallow circuit. So in fact, our encoding and the whole quantum circuit is just 2 gates in our solution. So that's a very important part of our solution.
All right. So we're 1 minute over time, but if somebody else has another question. Otherwise, let's thank Aviral again. Oh, too late. Offline. Let's thank Aviral again. Thanks.
Thank you.